So I will talk about some of the work that we're doing here in innovative new approaches for designing joint cognitive architectures. Um, and specifically, I'm going to talk a little bit about the framework that we have here. It's a computational framework called Work Models That Compute that we've been developing here over the last 6 years. It actually goes back further. It was started by Amy Pritchett and Karen Fay at Georgia Tech in 2014. Um, and yeah, we've been working on this tool and the more general sort of conceptual idea around using computation and computational work models to better understand joint work and to then design joint cognitive architectures with these tools. So a little bit of context, what the domain that we're going to be talking about later in the presentation, but that also illustrates the challenge that we're addressing is we are doing work in disaster robotics. That is a domain that is characterized by highly unstructured work. Every disaster is different. The work demands are different every time. The work is highly dynamic. It's a highly dynamic operating environment. Oftentimes, events are still partly ongoing. There's lots of uncertainty about the impact of a disaster, and so you're constantly dealing with disruptions or unforeseen circumstances. And we have in these disaster response operations. We typically have highly expert and skilled practitioners working, first responders, search and rescue teams, not astronauts and pilots. This is a more general thing that we also work in other domains where we are also coping or dealing with expert and skilled practitioners like astronauts and pilots. We also have in the context of disaster response operations, typically when we talk about human machine systems, that we are interested in designing, that human machine system is rarely one person working with one machine or one robot or one UAV. It's often usually it's actually multiple operators working with a robot or a UAV, but also that human robot system is part of a larger operational system where interdependencies with other entities within that bigger organization matter for the work of the human robot system. So, for example, a search and rescue team that uses a drone to scout an area and identify any signs of potential victims, they are part of a larger system that also includes ground teams that they will need to communicate with and coordinate with. And that actually creates a significant portion of their work demands. So when we're thinking about how we are designing these human robot or human machine architectures for contexts like this, actually drawing the system boundary a little wider is important for us to think about the kinds of coordination that we need to support in our human machine system design. So our focus is on developing new methods for designing joint cognitive architectures of human and machine capabilities while considering interdependencies at scale. So I will talk in the first half about some of the conceptual ideas behind our computational work modeling. And then Sal is actually going to talk about some of the applications that we're doing in this work domain of disaster robotics. So to talk about the conceptual foundation behind our computational work modeling, I like to use this paper from 1994. So a while back, I recommend this as a read. It's a really good write-up of the differences when we think about design. We often use these terms of function, behavior, structure, and purpose. They do a really good job of kind of disentangling those and really laying out how they relate to each other. And so this is a graphic that is adapted from their paper. and it essentially describes for an artifact in a more general sense, how these different things relate to each other. So an artifact, as we're designing an artifact typically has some kind of purpose, right? There's a so what, like what is this artifact used for, or why is this artifact here? So that's the purpose in the context of a human social cultural environment. At the very bottom of this graph is the structure. That's actually what it is, right? It's physical structure, but perhaps also if we're talking more about software, it's computational structure, it's computational organization, it's code, and perhaps if it has some hardware, if we're talking about a robot, for example, it's sensors and it's actuators. And then in between, we have things that are really important that we'd like to link the purpose to the structure. And we can do that with two things. On the one hand, we need to define what it actually does, and that's the function. Like, what is this artifact doing relative to its purpose? And then also, how do we actually achieve that function by performing some kind of behavior, right? Especially when we talk about some machine capability or AI capability, it exerts behavior, and that should affect the kind of function that we'd like it to have. It needs to be able to do the things that we want it to do. So this is just talking about a single artifact. When we're talking about a joined cognitive architecture, we sort of adapted this framework and split it into a multiple where we now no longer have just a single artifact, but we actually have maybe a joint architecture where we've got human and artifact or human and machine jointly acting as a system that has a purpose, some collective goal. There's functions of the machine agent, of the artifact, but also functions that a human fulfills, important functions of filling contextual gaps or intervening or monitoring. And so we want to make explicit what those, like, what is it that the human does in that joint cognitive architecture? We have behaviors of both the machine as well as human roles, and we'd like those behaviors to be coordinated over time and synchronized over time. And then at the very bottom, we've got the structure where in joint cognitive architectures, the human and machine roles are structurally separated, but are usually functionally coupled. Right, so the structure is separate, but that functional layer there is really important because that's where a lot of the interdependence between human role and machine role really happen. And that interdependence creates a need to coordinate and synchronize work. So as a design time question, right, in this sort of conceptual framework, the key question is what is necessary to effectively manage these interdependencies, this functional coupling between human and machine roles under a range of operating conditions. So we're looking at existing models for supporting design. We were roughly able to map sort of two classes of models onto this conceptual framework. On the one hand, we saw models used in model-based systems engineering, for example, or digital twinning that focus a lot on the structure behavior relationship of machine parts of physical systems. Think, for example, how digital twins of aircraft have highly detailed computer models of the structure of aircraft, how all the different components relate to each other, and we can run computational simulations to evaluate their behavior over time. and to do verification and validation in a design context. We also see on the human side existing computational models that are used in a design context. For example, ACTAR or SOAR are cognitive architectures that include models of the structure of the mind, of a sensory system, software modules that mimic memory or attention management, and that can be simulated computationally to evaluate some aspect of cognition, whether it's workload or human error rates or human failures, right? And do that in the context of design. What we're seeing as a gap, though, is that none of these models really make explicit what the functional coupling is in a larger joint cognitive system and how interdependencies really matter between human and machine agents. And that's really that second layer from the top that we don't see well accounted for in existing design approaches. So this is where our computational work modeling fits in that yellow box here, where our work models take a more holistic view of the work that needs to be performed. So first and foremost, we model the work, how that work then is distributed among different entities within the joint cognitive architecture, and how that work is then coupled and interdependent. And that helps us identify what is necessary to coordinate multiple threads of interdependent activities. And the way that we make it computational is by using graph theory and then dynamical systems theory. So at the functional level, we model functional coupling as a graph, a network model of functions and resources that capture both what needs to be done, but also how there's functional coupling between multiple roles that will need to be coordinated. And then at the behavior level, we're actually able to take these graph models and simulate them over time so that we can evaluate how well multiple threads of activity are synchronized over time relative to each other, how human and machine roles might need to synchronize their activities with each other, but also that there's, especially in things like disaster robotics, that there's events in the world or dynamical processes in the world that the human machine system needs to keep pace with. And so we can model how well a potential human machine system architecture would be able to keep pace with some of those environmental dynamics. I kind of skipped ahead a little bit here. So this is what the formalism looks like. We have graph theory at the functional level that captures some of the interdependence relationships. And then we have an ability to simulate and look at action traces and time traces of activity and see how well activity is synchronized or coordinated. So this is where we our modeling and simulation tool, work models that compute lives, and we are developing this as an exploratory tool. So not as a verification or validation tool where you've designed your whole joint cognitive architecture and then at the very end you do some verification or validation exercise. We actually think of these kinds of models as being tools really early on in the conceptual design stage of a joint cognitive system, where the tools are helpful to explore interdependencies. And so part of our model is actually, or of our modeling, is to make them really highly reconfigurable so that you can easily play these kinds of what-if scenarios and try out different potential architectures and different distributions of work to try and understand where interdependencies really play a role and how they might impact the overall performance of your system. So these are some of the questions that one might ask if you're using our modeling approach and you're using it as an exploratory tool, these are the kinds of questions that one might explore. So for example, right, what functions will my machine agent need to coordinate effectively? Or how will, if I have a certain machine capability in mind that I'd like to deploy into my disaster response operations, how might that actually transform human work? Will it lead to new coordination requirements that I'll need to somehow support or train for? If we have different distributions of work, different potential machine capabilities that we're exploring, how might those different distributions lead to different kinds of emergent behaviors between humans and machines, or different kinds of synchrony requirements or coordination requirements, and also fundamentally, right, what interdependencies between human and machine roles matter when. So I'm not going to spend too much on this. This is just a little bit of the formalism behind it. But this is the sort of the formal graph representation that we have of work. I will make a note here that we have these different layers within our models that capture how there's at the bottom two layers sort of a base set of work that needs to happen. That regardless of how you have designed your joint cognitive architecture, there are certain functions that need to be performed either by human roles or machine roles that are specific to that work domain or that context. But then based on how you actually define your human and your machine roles within this functional space, you distribute the work between multiple entities within your system. There's going to be interdependencies that need to be managed. And so the upper two layers, we're trying to make explicit what kind of work is necessary to manage these interdependencies. That there's usually additional work that needs to be performed within that joint cognitive architecture to coordinate and to synchronize activity. That might include things like monitoring what the other party is doing, or redirecting what another party is doing, or trying to project what the other party's behavior is going to be in the near future, so that you can select your own activities to be in sync with that other party. So by making that work explicit, we're hoping that makes it easier to then design to support those kinds of functions within joint cognitive architectures. And then we can make our work model computes by actually for all these different functions, defining their timing relative to the world, and also what kind of transformation that work function makes in the world. If there's questions about that later on, I'm happy to circle back to this slide, but I didn't want to go too deep into the technical side of things. My last thing before I'll hand it over to Sal to talk about how we're using this in disaster response operations is to just sketch out sort of the high level process of using computational work models as an exploratory tool. So we have our formalism here, our definition of the work that needs to be performed, and then we defined it in a way that makes it easily reconfigurable, that we can test alternative human-machine teaming architectures or different joint cognitive architectures by distributing the work differently or changing the kinds of coordination mechanisms that we're envisioning. And then those two, both the base model as well as the model parameters, are input into our fast time simulation engine. So that will actually simulate the work over time. From our simulation engine, then we can do some post-processing to see how well the different threads of activity were synchronized or coordinated with each other, how much overhead was created for actually managing interdependencies. That's that additional work I was mentioning of monitoring others, redirecting others, or projecting the behavior of others. That there can be significant sort of costs of coordination associated with joint activity. And so as part of our simulation output, we can get some computational estimate of that overhead and whether the human machine system is actually able to reasonably manage that over time. And we can get some insight into how well the human machine system can keep pace with events or dynamics in the world that matter. An example here is in our space work, for example, we are looking at how to design human automation systems for managing emergencies on future spacecraft. And one emergency is that we have a loss of pressurization. And so there are certain dynamics there at play, the loss of pressure, that sets the required tempo. Like there's only so much time you have to respond effectively to that loss of pressure before you run out of oxygen or air. And so you've got to take actions early to maybe buy yourself more time, and then to be able to diagnose the situation, find the leak, and then resolve the leak. So in our simulation, we can actually, with different ways of distributing the work between humans and automated systems, we can evaluate how well the joint cognitive system actually is able to keep pace with those critical dynamics. So from this sort of the insight that we draw from the simulations, the most important thing I would say is this feedback loop, is to use insight from the models to reevaluate your assumptions in the models of what work is necessary and what coordination functions are necessary, or perhaps what joint cognitive architectures are effective or ineffective, and revise the model or revise your human machine teaming architectures and simulate again. Right? And this is the essential sort of exploratory aspect of it, that we really see this as an iterative process where you would start with a sort of an initial idea of what the work would be very early on in the conceptual design stage. One typically has some notion of the work that needs to be performed, maybe some idea of the kinds of machine capabilities that could play a role here, and then simulate early on, get some insights, revise the model, and do so iteratively, and in that sense, uncover more about the work that needs to be performed, the kinds of interdependencies that exist between the different roles, and what sort of coordination capabilities are necessary to support effective joint activity. Let me pause for a sec to see if there's questions before we jump into the application side of this.
We don't have any questions currently in the chat or the Q&A, but if anyone wants to raise their hand right now, we can handle those. Oh, Alex has raised his hand. Alex, let me take a look and see if I can unmute you here. Yeah, you should be able to talk.
Am I here?
You sure are.
Okay, perfect. So the only question I had right now is there's no sense of time, there's no sense of scenario situation yet. And I'm assuming that comes in the middle bit with the computational evaluation, but where does is there anything going on now or has gone on as the preparation work to say, here's the type of scenarios, time-based sequence of events that would lead to us being able to design a functional model of work as envisioned?
Yeah. Oh, thanks, Alex. Yeah, that's a great question. So on the we do use scenarios in the simulation in the middle part, indeed, and some, I think, scenario envisioning when we're actually developing the work model here. Although I guess this is a challenge in the modeling. We're trying to usually make our model a little scenario agnostic, that we're identifying the work um, not too specific to a scenario. On the one hand, on the other hand, I guess one often does need some scenario to get the ideating going on what the work is that needs to be performed. Um, so we're yeah, we are defining the work, I guess maybe in the context of a class of scenarios. Like for that space example, for example, we would model the work of what it would take to respond to the general emergency of a pressure leak. And then we could simulate a bunch of more specific scenarios where that pressure leak could occur in different ways, in different sizes, different places. We could insert other kinds of potential disruptions or anomalies, and in that way, sort of explore different scenarios. Does that help clarify where the scenario fits in?
Yeah, absolutely. Yeah, in my experience, it's the getting to the functional model is in some ways the most powerful thing, and in some ways, and not even in some ways, in most ways, is the most difficult thing,
Right.
and the most difficult thing for people to generate. And immediately, the first thing that I think I do, and most of the people I know, is immediately when they're trying to functional model, they're elaborating a set of possible cases, events, sequences of things to try to look for and identify what are the abstractions that would represent function. And so that's why I was just curious here. Starting almost in my head means thinking, well, what's the sequence of events that might lead to some situation? Okay, now what are the relevant functions? But I didn't see that here, so that's why I wanted to ask. And if it's in the loop, that's cool. It just means there's sort of maybe initialization condition that is, somewhat unique.
Yeah. 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 Good point. And I think what we're in further developing this approach, I think what we'd like to do is I think for this to be an effective exploratory tool, it needs to be highly reconfigurable. And that probably also means that the base scenario or the scenarios that you're testing need to be kind of highly, that you can easily reconfigure the model if you encounter a variation of the scenario that you hadn't thought of before. So anyway, that's a space that we're thinking about. How can we make this sort of easily reconfigurable so that we're not too connected to a single scenario, but that we can use it to explore a range of different scenarios easily and effectively. All right. Any other thoughts or questions before we move on? Okay. All right, Sal.
All right, thank you, Martijn. So I'll go into a little bit of our application of this modeling technique to something a little bit more concrete here in disaster response operations. So people have been using robots or drones in various capacity and responding to disaster response or disaster scenarios for 25 or 30 years approximately. And there's clear benefits to do so. Robots can navigate unsafe or inaccessible areas that people can't. They also provide additional sensing capabilities, such as we're seeing first responders using drones with thermal cameras at nighttime to help search for victims when it's very difficult for humans on the ground to be searching for people in the dark. However, we're seeing a lot of challenges to deploying robots, and we're envisioning a bit here into the future where there's not many autonomous capabilities being used to respond to disasters right now. However, we are seeing that there's a push to kind of make these drones or robots have more autonomous capabilities so that you can either use more of them or just make the operations more successful, hopefully. But obviously, we want to also be aware of the challenges of how automating or introducing automated agents will actually change the work and the operations itself. As this kind of play on Murphy's Law from Dave Woods illustrates, that whenever we introduce autonomy, especially into these very dynamic, unstructured types of domains like disasters, it introduces a real need to coordinate with these autonomous agents, so to speak. So the challenges of deploying robots that we're seeing right now is that the cognitive load of their use, currently when operators are using robots in these scenarios, typically in disaster response, you're going for the first 40 hours or so without sleeping or in very challenging conditions to try to find people within that very critical window when it first, after the initial fall of the disaster. So there's lots of cognitive load of using these under a lot of stress, and also coordination overhead arising from the need to exchange information with other agents in the system. As you can imagine, these systems typically are very widely distributed. There might be an incident command giving information or orders to the field. There's ground teams that are working. And then you have people with robots or drones also trying to search. But you want to make sure that everyone's coordinated to be efficient and also to be putting the effort where it's most needed. And we know just from cognitive systems engineering that coordination breakdowns often occur more often with automated agents because of the literal mindedness of them. And that is one of the things that we want to highlight with our modeling and simulation is that the coordination overhead, the coordination functions needed to synchronize activity between multiple distributed groups is not negligible. In fact, it's a very important part of these operations. And even though this is an example from earlier this year, it wasn't an automated drone, but it kind of underlines this idea of coordination being a challenge of this domain, is that a drone hit a helicopter during the Texas flood response. And that was extremely dangerous. And although it's a little bit ambiguous why exactly that happened, it underlies the idea that we need to make sure these automated drones or robots of the future are very much coordinated with other groups in the field. So I'll kind of outline two approaches to technology or system design. The first is basically what's going on right now with using technology for disaster response, which is you kind of have technology off the shelf, typically, or if you're lucky enough to work with the research group, they can perhaps design something specifically for your use case. And then it's up to the people in the field to kind of make the technology work, so to speak. And this is kind of ignoring the underlying functional model that we were talking about, perhaps ignoring the coordination overhead. It just, the people are grateful to have the technology. They are forced to make it work. And we're seeing that that's just not an optimal strategy from an engineering design perspective. What we are proposing is that a better way would be a systems first approach, which is starting with the design of the system first. And the detail at this level is in the connections between agents and the functional coupling between agents. And through understanding these interdependencies, you can identify what key coordination functions, what key information sharing requirements are needed for these groups and agents to work effectively together. And so we call this defining the parts based on the connections in the broader system. So we want to evaluate the technology based on, or choose a technology rather, based on what connections we want to support in the system. So beginning with the interdependencies of the work first. So here is kind of a visualization of this point. At the bottom, we have, let's say, the parts of the technology. You might have algorithms that help you classify victims with machine learning, or you may have path planning algorithms, and then it's given to first responders and other stakeholders in the system, and they basically just use it and make it work, so to speak. What we are suggesting is a top-down or a whole-to-parts sort of view, where we define the connections between how this system works, what information sharing requirements would be important between these groups, and then evaluate, and then considering our technology based on those connections afterward. And we have techniques to do that we're describing here, such as our exploratory modeling and simulation work, and I'll be describing that in more detail in the coming slides.
Yeah, I'll talk a little bit about this this model before handing it back to Sal. So this is work that we did looking at the work of navigating in a typical sort of search and rescue context where, in this case, we had some kind of location that we wanted to drive a robot to, but in a completely deconstructed or collapsed environment where we don't really know where we can travel, what the safe areas is, where we could potentially get stuck with our robot. And so we wanted to use our approach to reason about interdependence and synchrony requirements between an envisioned robotic capability and in this case a single human operator. Sal will talk a little bit later about how we could then expand the boundaries beyond that human robot system. So on the left side, you see in table form, and we'll go over all this in detail, but we created a functional model. The left two columns capture all the different functions, image capturing, robot movement, next waypoint selection, with some description on the right side. And then we defined kind of an architecture here by thinking through how are those functions distributed. So the robot has certain authority over those functions. There's human authority. In this case, they're managing the camera angle. And then there's some functions where human and robot have joint authority and that they both contribute to this function, like robot path planning, obstacle localization, and then localizing or assessing one's attitude. So on the right side, you see a visual of that model. The lower two layers capture all these different functions. You see in blue, darker blue, the robot authority, magenta, there's the shared authority, and then the red is the operator authority. And then the lower layer here is captures all the different information resources that these functions interact with, and that create interdependencies between the different functions and between the human and robot roles. And then the upper two layers here of this model show how then for this architecture, we defined a set of coordination grounding resources as well as synchrony functions. So we tried to make explicit for this distribution of the work what the kinds of information would be for the human and robot to effectively synchronize their work. That there's some need to understand the status of the robot's activity, that there's some need to have some projection of what the robot will do in the near future, and to also have some ability for the operator to provide directions to the robot here. So those are sort of the resources at the coordination grounding layer, and then the synchrony functions here captures the work involved in actually managing that coordination. So the need to monitor, to direct, and to project the robot's behavior. So with that functional model, we can do a bit of computational analysis even before we go to simulation. In this case, we looked at, from a graph theory perspective, eigenvector centrality. And so I just, given these are sort of, the labels don't say much inbound eigenvector centrality, so I put these little bubbles to them. The horizontal axis describes how much a function depends on other functions. And then the vertical axis is how much other functions depend on this function. So there's a little bit of sort of outbound and inbound sort of dependency here. How much for a given function does it depend on other functions, but also how much sort of downstream functions does it support? So the rightmost corner here are sort of the most central or critical functions here that apparently have they depend on a lot of other functions, but also there are other functions that depend on that function. So we see here in the figure that things like next waypoint selection and robot path planning, that those are particularly central here. And with the arrows here, I've highlighted some dependencies here, some interdependence in that we've got the robot path planning and next waypoint selection and sort of a key dependency here that, given its centrality in the overall work model, would require is what we would say here is would require a high degree of synchrony of activity. So we use that to dive a little bit deeper into that synchrony with the simulation of actually simulating this work model over time and exploring what sorts of synchrony requirements there actually are for this particular dependency.
Okay, so just to zoom out a little bit, again, so the goal of our simulation in general is to be used as an exploration rather than a verification or validation, as Martijn mentioned earlier. So as to uncover a range of feasible strategies and what trade-offs could exist within a given architecture as defined by the functional model. And I think it's important to note that any one run under one given set of parameters is not necessarily, let's say, a realistic run. And I'll explain that a little bit more and talk about the parameters. But this is the model. So it's a map of disasters. It's actually like a collapsed nuclear facility that someone simulated from a different study. And then we converted it into a 2D representation for our study. And we're looking at traversing this disaster area with obstacles. Could you hit the next one? So this is our environment, so to speak, is the map itself. And then we have the robot starts in the lower right-hand corner, and then it goes to approximately the top middle where that X is. And so it has knowledge of where the end goal is. So the parameters that we're varying in this run, or else it would just have a perfect knowledge of where to exactly go, is the look-ahead distance, number one. So you could vary it, let's say, from 2.5 meters up to whatever you want to make it, like 15 meters or so. And so the robot will only see the obstacles that are in its course within that look-ahead distance. So it does not have a perfect knowledge of the environment, at least in the beginning. And the other parameter that we're varying is how current the information for the path plan needs to be updated for the next waypoint selection. So the first assumption is that it's every 15 seconds, so that you need to update it very often. So it's going to be performing path planning. It's going to be reevaluating its path and planning that path every 15 seconds based on the new information since the last point that it moved from, all the way up to 100 seconds. So it'll wait 100 seconds before it reevaluates the path based on the new information that it's gained from moving in the environment. And below here, these two diagrams here are just showing the logic that Martijn was explaining on the other slide, where if we vary how often the next waypoint selection NWS is performed, let's say at the top from 35 seconds, so fairly frequently, to the bottom, which is 100 seconds, so almost double or more than double the amount, then we see all the downstream functions as well are being varied too because of the connections in the functional model. So this is just to demonstrate that the functions depend on each other. So in order to perform next waypoint selection, you might need to perform other functions to get the up-to-date information in order to perform next waypoint selection, NWS, in this right here. So as I was saying before, any one run in isolation is never a perfect, let's say, model of how it would actually work in the real world, because you can imagine your look-ahead distance is varying dynamically depending on what's immediately in front of you. If you look, let's say, out a window, you could probably see hundreds of feet away from you. If you look inside of a room, it's probably 10 feet. So it's always varying. And the same thing for how often you'd want to vary any function in terms of how often you perform that function. However, what we're doing is we are simulating hundreds of different trials and then looking at the aggregate of that information. That leads me to the next slide. And so the real goal of this is creating this kind of trade-off space so we're analyzing the aggregate of all runs to see what that reveals. So we plotted these runs here on this trade-off plot. And so the optimal runs represent the minimum amount of coordination for a feasible operation. And those are the runs that are starred on this dashed line. And we're hoping to show the thoroughness efficiency trade-off. So let's say we're on our y-axis, we have total information exchanges. And so in general, we want to be operating, no more or less than what's required to actually do the activity itself. And so this is kind of our optimal amount, is minimizing how much total information or coordination overhead we need to achieve for effective operations. And then on the bottom is look ahead distance. So what's the available information of obstacles that we have in front of us? And then with the color on the side is just to help contextualize what was the actual, how often was this function being performed? Was it every 30 seconds or every 100 seconds? And so what does this tell us? So above the line, this is showing runs or simulation runs where we over-coordinated. So there was lots of information exchanges. So we were performing path planning function many, many times, very frequently, and then we weren't risking a crash. Below the line, those red X's represent a crash within the simulation. However, more abstractly, let's say these autonomous robots, they have automatic object detection sensors that would hopefully avoid a real crash in a literal sense, but in this abstract simulation sense, a crash would just mean that an action was taken or function was performed with old information, so it is effectively not optimal. And so below the line is representing under-coordinated runs, and above the line is over-coordinated runs, but perhaps that would allow some more flexibility if those functions were performed more often. And this is this curve shows a range of activity as a whole that a system should be able to support. So if you were to imagine, let's say, a look-ahead distance of a few meters, you need to be performing these coordination functions quite often. And so the only feasible two strategies that are plotted here have very high information exchanges. So that represents a type of strategy in your design of the coordination between two agents that you need to be able to support when a robot would need to interact or coordinate very frequently with an operator. And then there's other times, maybe when the environment isn't changing so much, when you can see very far in front of you, the look-ahead distance is at 20 meters, then there's a lot more strategies that are feasible because the world isn't changing that much. So you'd also want to design interaction strategies for when less coordination is needed. So tell us just a little bit about the types of interaction patterns that you'd want to help support within your system for effective activity, and identify a few edge cases that you might want to test more in human subject trials in the further design cycle. So I'll go quickly through this. So we begin with the human robot team as our system scope, but we're finding that, especially in these distributed operations, that isn't enough to consider for coordination of that automated robot. So we can, if you want to click through a couple times, we can show we want to also include the search and rescue ground team, because there might be times where they want information requested from the robot team, such as, can you go look into this disaster area to make sure it's safe for us to enter, or to see if this area has people that's worth more immediate action for the ground team to look more thoroughly through. There's other times where incident command should be involved, where they would either give let's say a flight restriction on drones because a helicopter is coming through the area. So that's coordination that needs to be involved. So there's multiple levels to look at here. And I guess the point of this is hopefully that from a systems engineering perspective, we want to make sure to draw our system boundary at multiple levels to try to capture coordination across all these teams. And here, this is a bit notional, but this was kind of just brainstorming to show what are the actual technical implications of modeling coordination functions. So the model on the left, this is a functional model, but abstracted on a little bit of a higher level to inter-team coordination instead of just looking at the human robot team alone. And so the red bar up top represents general functions from the human robot team, the blue from the ground team, the ground search team, and then the teal box is incident command. And I simplified the model to only show functions that are sharing information that other teams would want to have. So let's say that the ground team cleared an area, and then they would need to have a way to coordinate with the autonomous robot. Hey, we cleared this area of people. Maybe that would affect the path planning algorithm of where the robot is going to go. Or let's say you have the drone with a camera on it, and then the ground team requests, hey, can you look at this area? You need a way to coordinate with the ground team in that case. Oftentimes that is not the case. There is no coordination available. There's no technology to support that. But we also want to consider the monitoring that people would need to do to see if there's something on the drone video that's worth exploring more, or evaluating the drone video for potential victims. And so this would require things like, let's say, a low latency video streaming infrastructure that may or may not be present to be shared with other teams outside of the drone operator themselves. Or also maybe, let's say, capabilities to mark points of interest on the map for further exploration, let's say from the ground team to direct the robot. So I'll stop there. These are just a few ideas for how the coordination that is being modeled in our functional model could actually lead to technical requirements for the system itself, I believe.
Yeah, and I think where we're going with this is we know that we did the sort of the dyad human robot, and we evaluated it in the computational simulation. We were able to identify this sort of, or at least reproduce this sort of fundamental trade-off in operational work, that you're kind of you're managing how far you look ahead, but that has implications for how much you actually need to coordinate with your robot. And so if you're looking ahead very shortly, like you're incurring probably a much higher load. You got to interact and iterate with the robot much more frequently than if you have the ability to look forward, further ahead, and it can reduce some of the information sharing load, and likely also the cognitive load for the operator. So this is just a first sort of example of it in the human robot case, and then I think Sal outlined how, as the next step, we'd like to be sort of expanding the boundaries and looking at interdependencies at a larger scale, and use these same sort of functional capabilities and simulation capabilities to explore interdependencies at this larger scale, and illustrate how that might eventually also have important design implications for your machine and your tech capabilities. I know we used most of our time. If there's some questions, we'd be really happy to hear them. We also have our webpage, and we also have a GitHub page that has Python toolkits that others can actually use this kind of graph modeling if they would like to. We're in the process of developing some toy problems so that people can kind of start with something simple and learn a little bit more about the formalism and the code before they dive and apply it to their own joint cognitive architecture design challenges. So thank you. I don't know if there's any questions or comments.
I have a question for you about the assessing the sort of over and under coordination. So the implication there is the robot's not learning in how you're judging whether it was over or under coordination. Is that correct?
Yeah, we're not. Oh, sorry. Hold on. Yeah, I'm unmuted. We're not assuming that there's any sort of learning on the part of the robot here. This is just a simple, relatively simple, like no learning robot. It just does its thing. But this would be illustrative of an operational trade-off that the operator would need to navigate based on sort of the environmental conditions that they encounter. That if by, I don't know, whatever sensor obstruction, or maybe there's smoke, or you're just not able to look around, like some obstacle, that implies that there's going to need to be a lot more information back and forth in exchange for the human and robot not to be acting on stale or outdated information, right? I think that was sort of the key. Like in the lower left corner here is the robot is traversing based off of a stale and outdated plan, and so like to collide or crash with some obstacle. And so at the same time, right, you don't want to be at the other side where you're kind of doing too much. You're interacting with the robot too much for what is strictly necessary by the environmental conditions that you've encountered.
Yeah, thank you. I think it just struck me that like what is considered over coordination if you're in sort of a learning situation could be seen as like an investment in sort of future performance as well, right? Like, so I'm interested in hearing a little bit more about how you will advance that idea as when it relates to working with AI or with learning models.
Yeah, thanks.
A couple of comments here from Aaron. Fascinating. Thank you. And Alex, you generated many thoughts and brought back many memories. I'm going to reach out. Thank you. It looks like we have no other questions. Thank you both so much. This was super fascinating, and I am sure you'll have a number of questions pop up in LinkedIn or other spaces. We have coming up on November 12th is our next seminar with Dr. Alex Morrison, who will be looking at applying CSE in the real world. And then we have December 2nd, Dr. Miriam Balkan and Dr. Jennifer Gallier will be talking about resilience engineering implementation strategies and using healthcare, excuse me, as a setting for that as well. So I did promise to drop the link for the upcoming webinars into channel, and I will do that now. Thank you all so much for coming, and we look forward to seeing you at some future webinars. Thank you so much, everyone. Thank you.